So hello everybody, I'm Sahraoui. I'm a PhD student. I'm actually finishing my PhD this year in deep learning applied to biodiversity data. I work at the ISIR lab in Sorbonne University and the National Museum of Natural History here in Paris. And I mainly work on natural language processing models applied to species descriptions and on multimodal models where I combine text and images in order to develop models that can help enrich the galleries of the National Museum of Natural History. So I think I can start directly the presentation. So I will be talking to you today about unraveling the potential of frugal AI for advancing knowledge extraction in species descriptions, which is one of the projects I worked on during my PhD. So this is the table of contents. At the beginning, I will be introducing the problematic to you and telling you more about the need to have text-to-graph models applied to species descriptions. And then we'll talk a little bit more about named entity recognition, and then I will present the distant annotation process that I have developed during this project, and then we'll go more about all the models that I have developed and the experiments I have launched in order to solve all the problematics that we faced, and then we'll go through the results of these experiments, and then we'll conclude on the results of the experiments. And then we can talk about if you have any questions, or we can discuss the results. So let's begin with the introduction. So to begin with, species descriptions are a really important source of morphological information that is used in biodiversity, by the biodiversity community. Species descriptions come in corpora like this one. Well, you can have fauna corpora or flora corpora, but I mainly focus on botanical species, so I will be focusing on flora corpora. Typical flora corpora will look like this. It will contain all the morphological descriptions about a specific species with the name of the species right here. And you will be having a lot of metadata also around a specific taxa like this one. And so there was a really heavy pre-processing step that I worked on at the beginning of my PhD in order to extract only the description of the species that you can see here and remove all the metadata. So typically these species descriptions are used by experts, by botanists, for example, in order to compare species between them and to identify if a specimen belongs to a given species, so which is called species identification. And the main problem is that it's actually really hard to go through all the species descriptions that are contained in all the floras in order to identify if a specimen belongs to a given species. And so what experts tend to do is that they try to translate the species descriptions into graphs, like you can see here. For example, this graph here, the blue nodes in the graph will contain descriptors, and the other colored nodes in the graph, as you can see in the key here, will contain names of the organs. For example, all the yellow nodes will contain names of organs that are related to the flower, and then you will be having the descriptor associated to a specific sub-organ here. So the idea by creating this kind of graphs is that we can compare several species descriptions between them, and it's much easier to identify if a specimen belongs to a given species just by seeing how many descriptors are activated, for example. And but the problem is that this is still really heavy for experts to do. It's really hard to take and to try to translate it into a graph manually. And here is where deep learning comes in hand. And that's why we have the need to develop a text-to-graph model that is adapted for species descriptions. So the first challenge we have encountered during our project is the absence of direct supervision and direct matching between our species descriptions and the graphs we want to extract from those species descriptions, which puts us directly in a context of distant supervision, which is directly linked to our team today, which is Frugal AI. So this context of distant supervision leads us to choose a task that we will be using in order to resolve this problem. And the task we will be choosing is named entity recognition, simply because named entity recognition is a well-studied problem in the context of distant supervision. And it's the task in natural language processing that requires the less annotation. And this is what we want to minimize. We mainly want to minimize the human intervention in the project and the need to have experts annotating the data because it costs a lot of time. So named entity recognition is a historical task that began in the 90s in message understanding conferences. It typically consists in identifying named entities and matching them with classes. For example, a named entity recognition task would be for this text, identifying the word Google here and associating it with the class organization, and the word American here and associating it to the class nationality. And what we have to keep in mind while doing named entity recognition is that we have to test our models in the two tasks that are the detection of named entities and the classification of named entities. So we will always be having two performances, the performances for detection and performances for classification. So now I will tell you more about the distant annotation process that I have developed. We all know that in order to train a deep learning model, typically in our case, a named entity recognition model, we need to have an annotated data set. In our case, it has to be an annotated species descriptions data set with each named entity that has to be annotated with the class we want it to belong to. So what we have done here is that we've created a process that allows us to have this annotated data set by minimizing to the lowest level the manual annotation and the intervention of experts. So what we did is that at the beginning, we took a glossary that contains only morphological related words like flower, tubular, white, blue, table, typically words that you can find in botanical glossary. And we've asked experts to annotate only those words without any context, just annotating these words and matching them with classes that we have chosen. These are all the classes that we have chosen. As you can see, this class is split into two partitions. We have the organs and the descriptors, which will help us, having these two partitions will help us afterwards create the graph based on the classes that are detected. So once the manual annotation of the glossary is done, what we do is that we project that glossary into our unlabeled textual descriptions. And thus we will have an annotated data set. This annotation is a distant annotation, so even though it helps us reduce the cost of annotation, but we have to keep in mind that the distant supervision can lead to noise in the annotations, since we highly depend on the length of the glossary here, and so this distant annotation can lead to two types of noise in the annotations. We will be having missing annotations because we may have words that should have been annotated but that weren't present in the glossary at the beginning, since it's not supposed to be exhaustive. And we will be having also ambiguity between classes. For example, we can have a word that can be associated to one class or to another depending on the context. But since the manual annotation has been done without the notion of context, we can have ambiguity between classes. So now, before I go to the methodology, I'd like to split maybe if you have any questions now, and then I'll go to the methodology. I don't know if that's okay with you.
Do you have any question?
Yes, maybe.
Yeah.
So basically, you're trying to do kind of transfer learning with a zero-shot transfer learning. So you're learning something on identity recognition and then transferring it directly to another task.
Actually, for now, this part is only creating the data set, and then we will learn train a model on named entity recognition. And then the last part is recreating the graph, but the creation of the graph mainly depends on the rules that we have created here. Since the classes we will extract will be, for example, types of organs and types of descriptors, only by using regular expression, we can afterwards recreate the relationships between the organs and their descriptors. I can explain afterwards the triplet reconstruction module maybe better, but for now, this is just creating the data set for named entity recognition and choosing the right classes in order to be able to reconstruct the graph from independent named entities afterwards.
Okay.
Okay. Are there any other questions?
Do you have a question online?
It's clear. Thank you.
Yeah.
Thank you, Sally.
Okay, so now we'll go through the methodology. So the baseline model that I've used for named entity recognition is the typical BERT model with a classification head that is a connected layer for keyword classification. So the BERT model depends on the transformers model, which depends on attention mechanism. And so this is the baseline. And afterwards, in order to overcome the challenge of the noise that is induced by distant supervision, we've thought about using self-training, using a teacher-student architecture. Well, basically how self-training works is that we will be having our baseline model that will be trained on our data set. And at each iteration, we will take some predictions of the baseline model, and depending on how reliable these predictions are, we will be adding them to the training set and the student model will be trained on the outputs of the teacher model. And at each iteration, we will be updating the parameters of our teacher model and so on. So this helps add more data to the training set and avoid overfitting on the initial training set, which was annotated distantly, and that avoids overfitting on the noise that's present in the training set. So are there any questions maybe about self-training?
Actually, I didn't get really what you said. So you train the model to extract the named entity recognition, but I really don't really understand the difference between the student and the teacher. Actually,
Okay.
What's specific?
So at the beginning, at first we will just use a baseline model and train it on our data set. So now we have a baseline that is trained on named entity recognition on our training set that was annotated distantly. What we will do is that at the beginning.
So you train on all the data sets, and according to the classification you have done with your distant annotation, so you can have some words and flowers and so in different categories.
Yeah.
And of course, since you said that it's not exhaustive, you miss a lot of entities.
Yeah, there are a lot of false negatives. And then so what we do is that at the beginning of self-training, so the first phase is only training a baseline. The second phase is self-training. At the beginning of self-training, what we do is that we give, for example, a sentence like this one to our teacher model. It's actually a batch of sentences, but to simplify it, let's say it's a sentence. We give it to our teacher model, and then the teacher will output some classes for each word here. And then we will, depending on how reliable this output is, just by checking the, just by having a confidence threshold. If the confidence threshold is, for example, higher than 0.9, what we do is that we say that the teacher may have been right about this prediction, even though the word wasn't annotated at the beginning. Maybe the teacher is right that this word should be a named entity, and we will be adding it to the training set, and we will be having the student that will be trained on this new training set that has new examples that were detected by the teacher, and we do this iteratively. So if we have 100 epochs, at each epoch we have new detections that are added to the data set. And then, so at each iteration, the teacher predicts some predictions. We use them, we add them to the data set. We train the student just one iteration. We take those new parameters and update the teacher student with those new parameters, and then we have another prediction and so on.
So the student becomes the teacher at each.
At each iteration, we replace the parameters of the teacher by those of the student.
Is it possible that there is a performance degradation on the pseudo label that you?
Actually, it's really hard to regulate the training of the teacher and the student. So the idea is to have a good baseline at the beginning, but the baseline should have a good recall and not a really good precision in order for it to detect more words than those that are present in the training set. So the teacher needs to have a good recall and at the beginning, and you have really to check the performances of your model at each iteration. And there is a drop at some point, so you have to know, you need to have an early stop in order not to drop your performances.
Okay, because you cannot always check the performance in the initial data set.
Yeah.
So, okay.
Yeah. What we do is that we check the performance on the new data set, but the idea, I will go to the testing strategy that we have developed in order to have a test set that is actually more representative of real world cases, and that helps us know if if our model is actually learning to detect new words or not. So this is what we have. Developed in order to overcome the challenge of the noise induced by distant supervision. And so another challenge we have encountered is the specificity of the vocabulary in species descriptions. So species descriptions mainly contain words that we cannot find in typical open domain texts. So the language models such as BERT-based and so on are trained on open domain data. So they are not really suited for this kind of text. So what we proposed in order to overcome this challenge is to simply pre-train the language model on an unsupervised task, such as masked word prediction here. For example, masked word prediction is simply given a sentence to the language model and masking a word and asking the model to try and detect that word. So once we have pre-trained our language model, we use it, we fine-tune it and add a classification head and train it for named entity recognition. So now that we have a model that can extract named entities from a typical sentence like this one, so what we have done in the pre-processing step is that we have created a pre-processing module that helps us sample our text to sentences that are focused on only one organ. For example, this one is focused on only one organ. So our preprocessing script helps us get only sentences focused on one on one organ, and then we apply the named entity recognition model that we have trained. Once we have extracted named entities from this sentence, for example, like here you can see that the model extracts the named entity calyx, valvate, and campanulate, so it detects that calyx is an organ, that valvate and campanulate are descriptors. So what we, and it will detect that valvate is actually of type disposition and campanulate is of type form. What we will do in order to reconstruct a triplet using those independent named entities is that we will use this simple rule here. So a triplet will be constituted of the main organ, the descriptor, which is, for example, here, the type of the descriptor, which is disposition, and the value of the descriptor, which is valvate. So, for example, from this sentence here, we apply named entity recognition, and then by using this rule, we will be extracting these two triplets, calyx disposition valvate and calyx form campanulate. And we do this to all the sentences of our species description in order to construct a list of triplets that can be represented as a graph. As well, I'm going to show you exactly how it's done afterwards. So now I will be first be presenting the results of the named entity recognition models, and then I will be presenting the results of all the framework, which is the graph extraction from one species description. So at the beginning, as I said, the problem in distant supervision is that we have a lot of noise in the annotations. And what we have seen is that in a lot of named entity recognition data set, there is an overlap bias between the training set and the test set. We will be having a lot of words that are present in the training set and present also in the test set. Well, the sentences are different, but there's a high overlap between the words, which constitutes actually an issue because we can't know if the model is learning to detect new words or is just doing retention of the words it has seen during the training phase. So to avoid this, what we proposed is that we create two test sets. We will be having a typical test set like all the other named entity recognition data sets, and we will be having a test set XC here that will be containing only sentences that contain words that were never seen in the training phase. So if we have a good recall, for example, on XC, it means that our model is able to detect new words that it has never seen. And a good recall here is a good recall on the classic test set means that the model is able to reproduce what it has learned. So these are the results on the classical test set, which contains words that were already seen in the training set, but in a different context. We can see, for example, here that that with self-training we have a high improvement of the recall and of the precision, so an improvement of the F1 score in general, and that the use of language model pre-training also brings an increase in recall and in precision, but the combination between the both gives us a small drop in precision compared to the self-training, which may be explained by the fact that combining pre-training the language model and self-training can lead to overfitting on the training set. So these two methods are better used separately than combined together. So these are the results on the classical test set. And now we present the results on the out of distribution test set, which is the one that contains only new words. as we can see here, the best performances are obtained by the self-training method, which so actually in this test set, the metric that is most important is the recall. We don't really focus on the precision, because the recall means that we are detecting new words, and the idea is to try and cover all the words that are present in this test set, since it's only named entities that weren't seen during the training phase. So the more named entities we can detect, the better our model is performing on this test set. And we can see that the highest recall in this data set is obtained by self-training. So now we will be presenting the results of our model with self-training on all the framework, actually on how it performs for extracting a graph from a species description. We can see here, for example, the species description of Burmania tenella. And for example, here we have this sentence here that is focused on one organ, which is ovary, for example. And so by our by our pre-processing script, we were able to split all this text into a list of sentences that are all focused on one organ. For example, here we apply our named entity recognition model on this sentence, and we apply the reconstruction module that I have presented before on the named entities that are extracted. And we can see that from this sentence here, we extract those nodes that are here. So we extract the word ovary, we extract the word globose and ovoid, and we have the types of the descriptors, which are form for globose and form for ovoid also. So we just by applying our framework, we can create these nodes here, and by doing so for all the sentences we can create this graph here. So do you have any questions maybe on this part?
No, that's quite impressive actually. Just you don't you just use the words, so you don't use the metrics that we see 1.3, 1.6, and so on. That's you get rid of that.
Yeah, actually, we only use for the idea is to. It's one of our perspectives to be able to add to our graph quantitative values, but for now, since it's named entity recognition that we are using, we only focus on morphological named entities and try to extract them.
But still, it's still the close description of the species, because you know that's for example the ovary of this one is ovoid or globose. You can have all the species where it's only ovoid and you don't have globose, so you get the structure of the description of the different.
So by translating the text into a graph like this, we can have several species and try to, for example, get all the species that for whom we've detected the name ovary, and try to compare all the descriptors of the ovary of several species and have a comparative. Actually, it makes species descriptions more comparable and more measurable. That's the idea. I think there's a message in the discussion. I'm not sure.
I might have a question, please.
Yes.
Yeah, sure.
I'm not sure maybe I missed the point. As for the measures of the performance, you talked about more recall and less precision. So at the end, there will be experts that would validate the results of the extraction, or it is not very important to have it's not very critical to have errors in the extracted information. This is the point that I'm missing here, maybe.
Actually, with this data set here, this one was annotated by experts at the beginning, and we we only measure the performances on named entities that we know are named entities. So that's why we only take into consideration the recall, because these are words that our experts told us that they are named entities and that they should be detected. And we didn't give them to our model in the training phase. So the idea is to measure how much our model is able to detect these words or not. And afterwards, we have experts actually seeing globally the graphs that we are able to extract and see if the model is performing well or not. This is like a safety measure that we have in order to control the quality of the graphs that we are extracting. But in the test of named entity recognition, since we do have a data set that is annotated, and we've created that strategy where we have a test set that contains only named entities that weren't seen in the training phase, we don't check afterwards with experts to see if these named entities are well identified or not, since they were actually annotated at the beginning. I don't know if I answered your question.
Yeah, my question was for the real data, real world data afterwards. Let's say never seen data that was not annotated. How would be the final system working for the users? So yeah, you've already answered the question. Thank you.
You're welcome. So yeah, the assumption is that this test set mimics the data that was never seen by the model, and we hope that it mimics it well and that it's representative of how the model can perform on real life data.
Thank you.
You're welcome. So as a conclusion, we have presented a named entity recognition model applied on species description by using a key value approach, where we have chosen classes that contain names of organs and classes that contain names of descriptors. And then we proposed a triplet reconstruction module that is based on those classes. And then we proposed a testing strategy for our named entity recognition models that is adapted to Frugal AI, where we had the test set that contains words that were already seen during the training phase, and one test set that contains only new words, in order to be able to measure the ability of our model to detect new words. And doing so, we have concluded that self-training is the best fitted architecture for our problem here. And so all this framework can be used in order to translate textual species descriptions into graphs, and which thus making species descriptions measurable and comparable. And it also provides us with language models that are adapted to species descriptions that can be used to other problematics afterwards. For example, right now I'm working on creating a research system that is adapted to species descriptions and specimen images, in order to be able to do some image retrieval on specimen images just by using descriptions of specimens, which can enrich the galleries of the museum, and so on. So the language model that is developed can also be used to several other taxes that are related to biodiversity. Thank you for listening, and I'm here to answer your questions if any.
So you're using a graph that's in the use case of a search engine, like if you want to identify what's the species, you could just use the triplets because you have the description. So what's the benefit of using a graph? Are there use cases that are really benefiting from the graph structure?
Okay, so actually the graph is more of a representation, like since it's like this structure, this format is used a lot in web data sets and so on. So we've chosen this format more as a representation, and representing it like this helps like put a lot of graphs of several species and compare them together, while like having lists of triplets, hundreds of triplets for a species is less easy to read and easy to compare. And in the graph, it's easier actually to represent, because the triplets will be contained in the name of the organ, the type of the descriptor here, and the type and the name of the descriptor, but will be missing, for example, the type of the organ, which can be represented here in the graphs by using those colors.
Okay.
So it's just an easier way to represent the triplets, but yeah, actually like storing them into triplets and then representing them as graphs, and we can use the triplets if we want for other tasks.
Okay, like distances between species.
Yeah.
You could compare between triplets.
Yeah. Yeah, exactly. Actually, even the embeddings of each word can be used afterwards to measure distances between species or between organs.
Okay. Thanks.
Welcome.
Online, do you have any question?
Yeah, I have two questions indeed.
Yes.
If I may,
Yes.
the first one is a follow-up of the question of the previous question, please. Is it related to ontologies and taxonomies, the population of taxonomies in general in semantics, or it is another way to construct graphs that is not really related?
Actually, well, this type of representation is used in systematics in biodiversity. Like they represent species descriptions this way, but I think they also use it in ontology. But I'm not quite sure if it's the same thing. But
Okay.
yeah.
Because it gave me some memories about historical work I've already done on ontology, so I thought it might be similar. So okay, I'll move to my next question, if I may. You talked about self-training, so it is a semi-supervised machine learning technique with a few amount of annotated data as a frugal technology. Did you test another way to do the same thing? I'm just curious about the choices that you had before you chose this way of training.
Actually, what we have tested is our baseline. We have the baseline model. We have the model with pre-trained language model, the model with some self-training, the combination of both. And I've also worked on a deterministic module that I add like to the to the outputs of the baseline, where I take into consideration the co-occurrences of the classes, something that looks a lot like Markov chains, but that can be applied not to a sequence, but to separated tokens.
Okay.
And I have actually, we had some promising results using this method on species descriptions, but since we weren't able to validate this method on other data sets, we actually limited our article, at least this one, to these techniques.
Okay.
But I'd be curious to know what kind of other methods you have in mind, maybe.
I thought about few-shot learning too. There are some architectures that need not too much data to learn. I don't know if it was suitable for your problematic, but I thought about it, and I was curious to see if you to know if you have already tested it or not.
Yeah, actually, maybe it would be interesting to test something like GPT-3 on this data, but not by doing named entity recognition, but by trying to create an annex task and use it like that. But since I began my work in 2020, It wasn't like GPT wasn't as trendy as it is today, and it wasn't like in our focus to use it. But it could be interesting, actually.
Okay. Thank you.
Thank you.
Online, there is question or not? Amina or Takaya?
I'm good. Thank you very much for the presentation.
Maybe
Yeah,
one or
okay.
two more question. So the frugality is located in the inexpensivity of labels at first, and in the fact that you can generalize to out of distribution. Is that so?
Actually, the frugality is located in the fact that we do not have, like we don't go from a direct matching from our species descriptions and the graphs we want to extract.
Yes.
So we don't have this connection. And in the fact that we don't have actually an annotated data set for named entity recognition neither. So we do it in a distant manner. And I think it's all the fact that we go from a case where we do not have annotated data, and we try to minimize the intervention of experts in the annotation process, and try to replace that by creating, for example, our triplet reconstruction module, and trying to shortcut it by going through named entity recognition with key value approach. I'm not sure. I don't know if I answered your question.
Yeah, perfectly. And would you say that the self-training process accounts to trading's accuracy on your initial data set for generalization power? So you're trading some accuracy on the initial data set in order to gain accuracy on the out of distribution data set?
Yeah, actually, it's a really good way to say it. I think that's it's trade-off between the performances on the data set we know contains noise and performances on a data set that we know we have to have good performances on.
Okay, thanks.
You're welcome.
Is that all for the questions? Thank you very much, Maya. It was a really clear presentation, and it's really nice work. And if I mean online, you will not be able to join us, but I've planned some drinks, so we will go for drinks and have a nice evening online for those who are online. And
Have a nice evening.
And see you for the next workshop. So we have a workshop next week on the 5th on the Bayesian network, and the 13th will be also on a few annotated data, but not in NLP, but on the computer vision. So you are welcome to register if you want.
Thank you very much.
Thank you, everyone.
Thank you. Have a nice evening. Bye-bye.
Bye-bye.
Et du coup là, avec les images, dans ce que tu veux faire, c'est être capable, à partir de tes descripteurs, de ta description en graphe, d'être capable de reconnaître, de faire la reconnaissance ou d'aller chercher les bonnes images.
En fait, c'est plus un moteur de recherche parce qu'on a l'herbier au muséum, il contient 5 millions de planches d'herbier, donc 5 millions d'images.
Ouais.
Et la seule information qu'on a, c'est l'espèce qui est associée au spécimen. Mais on n'a pas